So this is my first time at UKNOF, and I was a bit nervous, sort of putting up the pitch, whether it would actually fit in with the rest of the agenda. I'm still a bit nervous about that, but I guess the program committee accepted it, so I'm kind of blame them if you don't think it's right. I'm even more nervous. Well, I'm particularly nervous now. I'm even more nervous about the fact that I'm last, and I'm literally the person standing in the way of beer. So hopefully you will find it interesting, and hopefully I won't talk for too long, so that you can get your refreshments. As I say, I'm going to talk about virtualized data center networking, and in particular a project that I've been working on for the past 18 months called Project Calico. So if we think about the data center, we're on the PDF rather than the PowerPoint. Okay. If we think about the data center, what we're trying to achieve is hyperscale efficiency. People are now talking about building data centers with tens of thousands of servers. And in particular, when we're talking about virtualization, we're thinking about hundreds of thousands of VMs or millions of containers running within those data centers. If you look at the sort of costs of data center and virtualization, it's gone down rapidly over the past 4 years. So it's sort of a third of what it was 4 years ago. So that means that a lot of people are trying to move their applications into the cloud. Virtualization is a big thing, and obviously when you're moving all of these workloads into the cloud, one of the things you need is the networking backbone to be able to support that. Quick quote from Einstein, the idea that you should make everything as simple as possible, but no simpler. That would be a mistake. So we're going to look a little bit about, well, how's that worked out for some of the virtualized networking technologies that are there at the moment. So, first one, how many people are familiar with containers and Docker? Okay, good. A fair few. Throughout this presentation, I'm probably going to talk about workloads a lot, and what I mean there is either VMs or containers, whatever your bag happens to be. If you were looking at Docker maybe 6 months ago, and you were starting off Docker and looking at the networking that you get out of the box there, you'd have this port forwarding and NAT solution, which was very simple. Einstein would be pleased for that. It worked out of the box, and basically what that gave you was the idea that all of your workloads on a particular host share that host's IP address, and then the Docker host is just providing you with some port forwarding. So if you've got two containers, maybe you reach one of them by pointing your browser at the IP address of the host, port 80, and you reach the other one by pointing at port 8080. I'd say that's great, and for people who are just playing with Docker, trying to get some containers up and running, that was a simple solution. But it didn't provide you with real IP networking. If you're running two containers both wanting to be running web servers, well, you're kind of going to expect that you could reach either of them by pointing your browser at an IP address, port 80. Not in this scenario, because obviously only one of them can expose port 80 on the host. A lot of types of application wouldn't work. You fundamentally meant you needed to know, well, how is that port assignment going to work? So yes, it was fine if you just wanted to try out Docker for a little while, but no one was going to accept that as a scalable networking solution for containers. So in the Einstein example, it's simple, but it's actually a bit too simple. The other kind of virtualized networking technology that's very popular is the concept of the overlay network. So this is something that's been around in VMland for ages. In OpenStack, there are a lot of different networking technologies using overlays, and it's coming to the container space as well. So here we're connecting each container or VM to a virtual layer 2 segment. So we're simulating a layer 2 network, which is we're overlaying on top of the actual network that you've got between your compute hosts. And there's different technologies that you can use there, GRE, MPLS tunnels, VXLANs, whatever. There's a whole load of different options there, which has a lot of advantages. It means, for example, if you have separate you want to separate your production network from your test network. You can create two separate VXLANs or two separate overlay networks, and therefore you know that containers or VMs that are connected to the production network are never going to be interfered with by the ones that are connected to the test network, because they are separate networks. However, it also has a lot of disadvantages. In particular, depending on the technology you're using, there can be a lot of state involved. Some tunneling technologies, you might have 1,000 machines, and suddenly you've got nearly 500,000 tunnels connecting those mesh of machines together. If you want to break out from one network to another, you need to start having the concept of on-ramps and off-ramps. So instead of your production and test network, maybe you've got an enterprise and you've got the accounts network and the engineering network. And normally you wouldn't want them to communicate with each other, but accounts do happen to have some need to display people's pay, and they have to have a server that the engineers can get onto. In order for that to happen, you've now got to break out of the engineering network, decapsulate out of whatever tunneling technology you're using there, go over on and re-encapsulate back onto the accounts network. And this gets particularly crazy if you can imagine scenarios where you've got two VMs running on the same host, and they just happen to be on separate virtual networks. To communicate from one VM to the other, you've got to go out to a whole different service somewhere else, some routing service that's going to decapsulate you from one technology, recapsulate you onto the other, and send you back. Where you're sitting there thinking, I was on the same host, and so it's potentially inefficient for the data path. So in terms of the Einstein example, it's maybe not as simple as it could have been. OpenStack gets a bit of a bad press for its networking, and they're trying to do a lot better. But fundamentally, OpenStack's been around for a long time, and networking in OpenStack has been a pain, and there have been people who have been prepared to say that publicly. So, if we go back, thinking of that OpenStack complexity. This is a picture that pulled out of the OpenStack docs, admittedly a couple of years ago, but this is one compute host. The yellow box, that's one compute host. And these are all the different interfaces and bridges that you need to get to in order to get a packet from VM at the top out to the network at the bottom. So, in that Einstein example, there's an awful lot of complexity there when really all you want to do is send an IP packet out of the box. So, we took the case of thinking, within Calico, say, well, let's step back and think about what are the actual requirements for virtual networking. Top requirement, workloads need to communicate with each other. That's pretty standard. You also want to have some sort of policy. So, the example I gave of the prod and the test networks, that is a good thing. Being able to say that these workloads can't interfere with these other ones, that is a good thing, and that is a requirement that people need, especially when you're building data centers. Maybe you've got a whole load of different tenants that you're selling your space to. You want to be able to make sure that one tenant's traffic isn't interfering with someone else's. The other thing we thought, though, was that the base requirements are, particularly in the modern data center, with web scale applications, the base requirement is that you need IP connectivity. People don't really care about layer 2 connectivity. There's not a lot of Apple talk going on in these modern applications. As an app developer, you just want to be able to send some IP traffic from your web server to your database backend, or wherever. So this is what we thought about, and we decided to try and take those requirements and build Project Calico as a data center virtualized networking technology that would sort of fit those things. So the idea is, we wanted it to be very scalable. As I said, data centers these days are getting up ridiculous sizes, and the number of workloads that you need to network together are just, let's say, 100,000 is drop in the ocean. We wanted it to be simple. We wanted that Einstein moment that it's simple enough, but not too simple. We also wanted it to be secure. So if we take the first part of that, scalability, we were looking around and thinking, well, are there any examples of networks that exist today, or 18 months ago, that have solved the scalability problem? They actually scale to that, millions of workloads. We racked our brains for a bit, and then thought, oh, hold on, there's a thing called the internet. So what if we built a data center like the internet? Without, you're probably aware of the general idea of how the internet works, but the point is, very simplistically, you've got a lot of hosts with IP addresses. They're all connected to routers. The routers are all connected together, and they distribute the addressing information around. And lo and behold, your host on one side of the internet can talk to the host on the other side of the internet because it knows how to get there. So we thought, well, what if we can sort of bring that down into the data center? So we've got the same picture. We've now taken it down a level. The blue boxes here are your compute nodes, your virtual hosts. So instead of individual servers at the top, we've now got VMs or containers. But again, let's give each one of those its own IP address. Let's connect them all to a router. Then let's connect all of those routers together. And lo and behold, through the wonders of BGP, your container at one end now knows how to contact container or application at the other end. And this is Calico. The idea here is there's no overlays, there's no encapsulation. This is a flat network. We've just extended out the network you already have between your compute hosts. We've just sort of extended that out to the to the VMs or the containers. So that's the scale situation. I've just said that's great. You've now got this flat network, so everyone can all of your applications can basically talk to all of your other applications. So that's brilliant. However, we also said that one of the requirements was that you couldn't do that because you wanted to have these sort of production networks and your test networks or your different tenant isolations. So what you really want there is some sort of policy. What we're talking about here is coarse-grained policy. So that is that very basic, I have my test network, I have my production network, I don't want them to be able to communicate. In the traditional approaches we talked about, that just happened by default because you had different VLANs or whatever. In Calico, we've separated the concepts of the network topology and the security topology. So as I said, from a network perspective and a reachability perspective, it's all one big flat network. And then we provide a policy engine that you use to say, well, these workloads are in my production network. We tag them with prod. These ones are tagged with test. And my rule is prod can talk to prod, test can talk to test, but they can't talk to each other. That's fine, and that gives you that coarse-grained capability. However, we'd kind of like to be able to go a bit further than that and talk about fine-grained capability. So if you imagine the people hopefully familiar with the ideas of microservices and this big sort of movement to simplifying your applications rather than building big monolithic applications that are very complex. You split your application up into very small pieces that have very defined purposes. So maybe you have a service which is your web front end. Then that talks to a database piece, and that talks to a bit of business logic or whatever. It would be great to think that from a security perspective, rather than having the situation that if someone hacks into my web front end on my production network, they've now got into the castle. They can now break out of that and attack anything else on the production network. Instead, if we could say, as an application developer, I know that my web front end should receive traffic from the internet on port 80, and it should only ever communicate with the database service on port 5391 or whatever. Any other traffic, well, it should not exist because I wrote the microservice and I know that's all it's ever going to do. So what Calico allows you to do is actually have that policy definition right down to that level. Rather than just saying, oh, I want to talk to any tag that's prod, you can say, no, for this particular container, I only want to be able to talk to things that are tagged prod database and only on port 5391. egress. Maybe you also have a rule in there that says on ingress, I'm happy to speak, talk to anyone from the internet on port 80, but no one internal on port 80. That should never happen. So Calico provides you with that sort of very rich, rich policy language. But the way we do that is through what we're calling the distributed firewall. So rather than having a firewall services that are running within your network and enforcing this policy, the best place to put this policy is as close to the containers or as close to the VMs as possible. So on this picture here, we have a compute host. It's running some workloads. Each of those workloads is exposing an interface. And then we're putting the firewall right on that interface, the particular bits of the firewall that are relevant for that container. These firewalls don't need to have 500,000 different firewall rules that are for all the different traffic. All that container cares about is, well, what should and shouldn't be allowed to hit me. So looking a little bit closer at the way we architect that. A big part of Calico was to not reinvent the wheel. If you've already got pieces in your system, or there's already open source pieces around that you can use to build this, well, let's use them. So this is a Linux host, and it's got a kernel. The kernel, turns out, is a great router. You can put 500,000 routes into a Linux kernel, and it will quite happily route your traffic all day. It's not going to be phased. The Linux kernel also has a thing called IP tables, which is a really great firewall. That's something that a lot of firewalls that you'll be putting into your networks, under the covers, they're using IP tables for that firewalling technology. So what we can do is, using the Linux kernel, we can use those pieces and provide that virtual firewalling function that I talked about. And the way we do that, we run an agent on each host, so this agent called Felix, and it's responsible for programming both the local routes into the routing table and the firewall rules into IP tables. But again, it's only interested in the pieces that are relevant to the workloads on that compute host. We have a distributed data store that feeds information into Felix. So we use etcd, which is basically just a distributed data store around the data center, and that piece has the knowledge of all of the workloads that are in the system. And then each Felix on each host is able to pick out and say, oh, well, I see, I've now got a new container starting up on me. I need to put a route in for it, or maybe it knows that the policy rules applying to some of the containers on it have need to be updated because a new database server has started elsewhere, and therefore it needs to make an update to the IP tables rule to say, oh yeah, you're now allowed to talk to this IP address. etcd gets that information from whatever orchestrator you happen to use. So that could be OpenStack, could be CloudSoft Brooklyn, Clocker, Mesosphere, Kubernetes, Docker. It doesn't matter. We provide basically we provide a plugin that works alongside that orchestrator and then takes that information, puts it into etcd to be fanned out to to all the Felixes. Then the other piece that we run on the compute host is a BGP client. So our friends earlier talked about Bird. We use Bird as the BGP client. Again, it's open source. It's there. It works very well. As the man said earlier, it's run at scale around a lot of the internet, so we know that works. And then Bird just picks up the routes from the routing table and redistributes those around the data center. So that could be to route reflectors so that they're then redistributed to other hosts, or it could be to your data center fabric. If you're running L3 in your fabric already, then you just distribute the routes up to, say, the top of rack switches. And because it's BGP, BGP has a lot of complexity to it, but we're using it in as about as simple as way as you possibly could. We're just using it to distribute routes around the network. But if you've got a BGP network in your data center, you can obviously take advantage of the expertise that you have there. You can do things like route aggregation, so you could decide to give each rack of servers a particular IP range for the containers that are going to run on there, and that way you can sort of limit the number of routes that need to be held in in each host. The options are there. In terms of the policy model, it's very flexible. It's sort of hierarchical. So each container or VM, say we refer to as a workload, and then each workload has one or more network endpoints on it. And then associated with each endpoint, you associate a profile. And then you build the profile out of rules and tags. And then you can reuse those pieces. It's a simple policy language, but it's also extremely flexible and extremely, you can do a lot with it. So that you can provide, say, that coarse-grain policy that I talked about, or also that fine-grain policy that you might want. So, in summary, nearly beer time. We think that with Calico, this provides you an option that allows a lot of scale. We've done, we've exhausted our budgets of testing on GCE, but run 100,000 workloads with no problem. Calico is designed to scale to millions of workloads with very minimal CPU and other overhead. Troubleshooting is very good. So with the Calico network, if you're sending a packet from A to B, no matter where you're looking at that packet in your network, what you will see is a packet from A to B. There's no encapsulation, there's no tunneling. In the overlay model, well, if you happen to be looking at the packet on the host that's being sent, maybe you'll see it from A to B, but maybe later on you'll see it, it'll be an encapsulated packet in a tunnel. The troubleshooting becomes very easy, and you can just use your standard troubleshooting tools. Everything is just flat IP. So, you don't think you can get from A to B, well, try ping, try traceroute. It's that simple. It's tools that people understand. You don't need the on and off ramps. I say, anything you want to do, you're just sending traffic to another IP address, and it's just a routable IP address. You can make use of things like ECMP and Anycast in order to do high availability. And from an application developer's perspective, you don't need to be a networking expert. You literally need to know the basics of IP and know that, I need to send traffic from here to here. That's about it. You don't need to have any DevOps knowledge to think, well, exactly what's the path? How is this going to fit into the system? It's basically all I had. I mean, I say it's an open source project. The main project website's up there. It's all on GitHub, so you can go and have a look at the code, have a look and play with it. We're integrated with OpenStack, but also I've got integrations with Docker, Kubernetes, Mesos. It's all up there on the website. We've got an IRC channel. We've got other contact information. You can talk to us on on Slack. But really, just very happy for people to download it, try it out, and see what you think. And obviously, we welcome any feedback. Thank you very much.
Any questions for Ed? No, looks like we're done.
Great, thank you.
Great, thank you.